Welcome. I want to say something about finite topology. We have worked in a framework which is very convenient also from a computer science point of view. We have a finite set of sets, we have a Dirac operator associated to this, and we have then a cohomology, and we can compute this cohomology which is compatible with the topology in the sense that if we take a product, then this behaves in the right way, like in the continuum. I'm wrapping up this paper on the fusion inequality, but while doing so, I thought this is actually quite a nice framework because we have a finite setup, finite geometry, and we actually deal with delta sets. We can deal with delta sets, which are just finite sets of sets, and then they are partitioned into S0, S1, S2, and so on. We have phase maps, and this gives us a cohomology, and we have then this Dirac operator associated to it. We can do computations. And what is nice about this framework is that we can really do products. We need products to do geometry. For example, we want to draw graphs, we want to have level surfaces of functions, of several variables. We want to implement that, and that only works if you can define a Cartesian product. And if you take a Cartesian product, there is one difficulty, which is that we run out of this simplicial complex. So what I really start with is a simplicial complex. A simplicial complex is a finite set of non-empty sets closed under the operation of taking finite non-empty subsets, and we have seen it has a nice topology. And the point of this whole, semester-long work was to see that actually for open sets this behaves nicely. For open sets we have also a cohomology. We can form quotients. We can identify things in this subobject. We can identify them, and so we can form then new spaces, new topological spaces. We have just to say how we do that. We have to say how we extend the topology. The topology, we just take the product topology. Here for the open sets we take the relative topology, and for the this is the one-point compactification, which is also well, and in this case we have also a way to just produce a new topology. So these are finite topological spaces. As we deal with finite topological spaces, and in each step when we extend things, when we produce products, when we produce quotients, and so we can carry on. And also important, of course, is to keep track which parts are S0, S1, S2, S3 in this delta set setup. And so this can be done by just assigning a dimension for every element. This is no more in general the dimension, just the cardinality minus 1. We have an example here of a product of two such objects. So each of these objects is a two-sphere. We take the product, we get the 4 manifold, and so the product has now 4 elements, but we have to say that this 0.48 is actually 0-dimensional. So in this case also, when we take a product, we just take the Cartesian product, but the Cartesian product of 2 points gives us a point in the plane, which gives us 2 coordinates. So this dimension has to be adapted. But that's no problem. That's no problem for the computer, and actually I've already implemented that in these 5 lines of code, which gives me the cohomology. I kind of keep track of in the code which I have. I have a simplicial complex or an open set, and I get from that the dimension. In general, when you take products, if you take quotients, you have to keep track of this, and but that's no problem. So the data structure of this such an object in this is a topos, because it's a delta set, it's a presheaf over the simplex category, so it's very nice object. It's what we do from a computer science point of view. We implement it by just having a finite set of set. we get from this also the Dirac matrix, which kind of implicitly gives the, this phase maps, it kind of encodes this phase maps, encodes together with the dimension the concept of a delta set. And then we also keep track of the topology. But that's kind of important. That's not, you cannot deduce that directly. We keep track of it. We have a little bit more structure on this, but we keep track of this, and we just define now a category which is the smallest category containing simplicity complexes, where we can do products and where we can do these quotients. If you take a simplex by itself, just a set like 1, 2 or 1, 2, 3, this is you can think about it as an open ball, as an open set. It's an open set. For example, a set with 2 elements, like 1, 2. That's an open set. So in this case, this is a simplicity complex here. We start with a simplicity complex. We write down the Dirac matrix. We have the Laplacian. We can compute the kernels, and we get the Betty numbers, which are the 1, 0. So now U is open. So this is a kind of an open set. And for an open set, for this open set, we have then just the Dirac matrix is actually a trivial 0 matrix. The Betty vector is 0, 1. Now U is open, so this is a kind of an open set. And for an open set, for this open set, we have then just the Dirac matrix is actually a trivial 0 matrix. Take the subset, so in this case, take the subset with just these 2 points. That's a 0 sphere. I identify this, and then I get a 1 sphere. So what I get, essentially, I have this open set, and so I've, with a 1 point, compactified it, and I got, so the G consists of 2 sets, and so this dimension here is 0, dimension here is 1. So if you look up what the Betty numbers are, they are 1, 1. So this is and then we have also to keep track about the topology. Whenever we do identifications like here, we have to keep track about the topology. So in this case, it's a finite topology which only contains the empty set, the set itself, and the set itself here, and this U, the original open set. So that's in general, we just take the original topology of the U which we take, and then we take the whole. So this is the 1 point compactification. Of course, it's not Hausdorff, but it's a connected space. We cannot split it up. We cannot write it as a union of 2 open sets. But if we take kind of products, like if I take the donut, if I take a 2-dimensional a donut, which is a circle times a circle, then this already kind of it matters whether you have to deal with 64 elements or whether you just deal with 4 elements. So here are some examples. So this was the 1 sphere. This is the open 2 ball. If I take the open 2 ball, the open 2 ball is just encoded right by this set 1, 2, 3. Now, if I take S2 times S2, which is one of the favorite manifolds, 4 manifolds of Hopf, because he asked whether it's possible to put a metric, a Riemannian metric on it, such that it's positive curvature everywhere. That's not known. Still no unsolved open problems. It's a simple space. It's just S2 times S2. And in this case, it is actually implemented by 1, 2, 3, by a set with 4 elements. Totally amazing that you can deal with this 4 manifold with a set with 4 elements. By the way, Kuhn is almost trivial in this framework here, because if you take a harmonic function on the product, it's just fxy. Harmonic function on the product is just a product of a harmonic function in x and harmonic function in y. So you can explicitly just give the cohomology classes. Also, the Stanley-Reisner picture is heavier in the computation. So especially if you insist, like I did always, I wanted always simplicity complexes, or even graphs. So, graphs from simplicity complex. Every simplicity complex defines a graph. Actually, every of these objects defines automatically a graph, where you just take the incidence. You take 2 points in this G and you connect them when one is contained in the other. The last example is here kind of just a 3 torus. So in this case, we can deal with 8 sets, because it's 2 times 2 times 2 sets. So this G here represents a 3 torus, But we have to say what we actually have with the dimension, right? So this point here, this is a zero-dimensional point. These are one-dimensional, the one-dimensional, two-dimensional. So we have to say what the dimensions are of these cells. We can keep track of the topology. In the case of a two torus, we have just the empty set, the whole set, this set, and so we have 1, 2, 3, 4, 5 elements in the topology. It's a very small topology, which gives us this structure. To summarize, if we look at this data structure of a finite set of sets, which comes from a delta set with has space maps, which has a Dirac then operator because we have an exterior derivative, where we keep track of the dimension, we keep track of the topology, and we do extensions. Starting with simplicity complexes, finite abstract simplicity complexes, we make the form products or quotients or whatever we want in any order. We stay always in this nice class, and we can work with it, and we have the nice properties which we want, like the homology, compatibility, and we have also a topology in each stage. So that's it for today.